For our double replacement reactions problem today, I asked you to predict and name the products of two reactions, balance the equations, and predict the states of matter based on a solubility chart that can be found in your online textbook, both in the text as in the chapter that addresses solutions and double replacement reactions, as well as at the back in the reference section. And of course, there's plenty of solubility charts online as well. So the first reaction was where we took aluminum sulfate and strontium nitrate, and we wanted to predict what's going to happen. So what we wanted to do first was predict the products. We assumed, because it is a double replacement reaction, that we will switch cations and anions. So we will have something called aluminum nitrate and something called strontium sulfate. At this point, we have no idea what the formula will be, because we have to balance charges first to determine that. So we need to identify the charges. In the periodic table, aluminum has 3 valence electrons. He's in what would be called group 3A under some systems, in the same column with gallium. And so as a result, it being representative, we can be pretty assured that there's no other charge that it would have. Sulfate, it always has a -2 charge according to any polyatomic chart you see. Strontium is also a representative metal. Strontium is an alkaline earth metal. The second column from the left on the periodic table, along with magnesium and calcium, has a +2 charge. Nitrates are polyatomics that have a -1 charge. We assume that because this is a double replacement reactions, these changes will stay the same. Anions generally always keep their charges, and because we're assuming there's no change of charge for our representative metals, they will also remain where they are charge-wise. From there, we balance the charges of each cation and anion pair to determine what is the actual formula for each compound. We know that the lowest common denominator of 3 and 1 is 3, so we need 3 -1s to balance a +3, so we have an electrically zero neutral compound. Strontium and sulfate are oppositely charged, +2, -2, so they need no other coefficients to make their formula. It's just SrSO4. From there, now we can balance mass. We assume that we're obeying the law of conservation of mass algebraically by counting up all of our particle representations. And when we do this, we're able to find a lowest common denominator that gives us the most efficient way of guaranteeing an equivalence of mass on each side of the arrow. And when we do a count, we see that with our 1:3:2:3 ratio, we have 2 aluminums on each side, 3 sulfates on each side, 2 strontiums on each side, and 6 nitrates on each side. Finally, when we look at a chart for solubility, we find that nitrates are generally going to be soluble regardless of what the cation is. However, although many compounds are at least somewhat soluble in water if they are in a sulfate form, there are some exceptions, and strontium is one of the ones that is listed as a sulfate compound that is generally insoluble in water, so we would presume that we need to put an S representing a solid precipitate form. So let's now move on to the next equation. So in our second equation, we were combining potassium phosphate and cobalt-3 chloride. And so we assume, once again, because this is a double replacement reaction, that we will have a switcheroo of cations and anions and produce something called potassium chloride and cobalt-3 phosphate. From there, we need to determine the charges so we can balance them and come up with the actual formulae of potassium chloride and cobalt-3 phosphate. So we do this by first making sure we know what the charges are on the reactant side, because it being a noble replacement reaction, we assume that each atom will have the same charge on the other side. Potassium is an alkaline metal, that first left-hand column on the periodic table, +1, no other charge possible. Phosphates are polyatomics, and like all other anions, tend to keep a stable charge when as an ion. We assume that cobalt has to be in the +3 state because it is with 3 atoms worth of a -1 chloride, so it needs to be a +3 to offset the -3 and be a stable, neutral, zero charge compound. So we bring these charges over here, and we can see that we have perfect matches, +1, -1. We don't need any additional coefficients for KCl. +3, -3, COPO4. So we balance mass charge. Now it's time to balance mass. And we can see here that the simplest way to balance both sides of this equation for mass is that we have 3 potassiums, 1 phosphorus, 1 cobalt, and 3 chlorides on each side, and so a 1:1:3:1 ratio works. Then finally, if we look at our polyatomic chart, our solubility chart, once again, we find that phosphates are generally insoluble except for a couple of our alkali metals. Alkali metals tend to make very highly soluble products. On the other hand, other metals tend to become insoluble in the phosphate form, and cobalt would be no exception. So in conclusion, in double replacement reactions, if we follow a very specific path, we can successfully predict the products, balance them for charge, and then balance them for mass, because we assume that charges will remain consistent on the reactant to product side. Once we have identified them properly, we do what we always do with compounds, try to make them electrically neutral, and then we balance for mass by finding the lowest common denominator that ensures that we have the same number of each element or each ion on each side.